hopefully you will not find it to be incredibly difficult. However, there's a graphing in today's lesson, so let's leave it at that. There's graphing. There may very well be graphing in your lab on Friday. In this unit, there's a couple of times where we would go to graphing. There is graphing today. For those of you who know calculus, the word tangent lines will come into play today. I'll be teaching it. It'll be part of today's lesson. So let's go ahead and first go over class schedule, and then we'll get to the lesson. Today is really the last big lesson of the unit. This is a short unit. I took a couple of the lessons out and put them into Unit 7 to make them more even. What does that mean? On Friday, you have pretty much the first half of the class. We're going to wrap up the unit. So we're going to have a short lesson, and then we're going to have a lab. And the lab will be on kinetics, what we're learning right now. One of the paper 3 style labs, Friday. Next week on Tuesday, I have built in a day of review. So we're going to have a full review day on Tuesday. I was considering the possibility of also doing another lab that day, but it really depends because my previous classes already have labs that day. It's too much to have set up at once. Like, I'll see. But Tuesday's going to be a review day. Practice on all types of enthalpy and kinetics. Enthalpy of formation, enthalpy of combustion, making cycles, all of that. On Tuesday, we'll be reviewing the unit. And on Thursday will be your Unit 5 exam. So it's coming quickly. And the week after next, we'll be back in organic chemistry, actually, for organic part 2. So make sure you have this tracked. I'm going to be working on the paper 1 practice questions. I have to double check to make sure I take out the other topics that I'm putting later on in the school year. So I'm going to look through those questions first before I post it. You can expect those questions to probably post by tomorrow night. I may get the time to do it tonight, but it's either going to be tonight or tomorrow night, and you'll have till next week to complete those. Remember the paper 1 questions you do on quizzes, that counts as a quiz grade. That'll be posted, like I said, either tonight or tomorrow night. Expect it to be posted by tomorrow night and due next week, before the test, of course. So that's going to go in your homework. There is good news about today. I'm not giving you new homework today, but the homework from last class is due, I believe I put it due tomorrow night. The reason why I put it due tomorrow night is because there was still one thing in today's lesson that I need to cover. That was question 7 on that homework. So if you weren't able to understand question 7 on the homework, I had not yet taught it. I'm teaching it right now. So before we do kinetics, there's one more thing in enthalpy, one more strategy, one more type of question that you could encounter. Let's go over the objectives for today before we get there. So what are we doing? Looks like a pretty hefty amount of objectives. What does that mean?
Very easy.
That means they're going to be hopefully easy to understand for the most part. Kinetics is a quick unit. In the new syllabus, Cambridge made it a little bit more difficult. They added a few additional objectives here, but it is still a pretty quick unit of study. I'm going to highlight what are the new objectives post-2022, because Cambridge does like to test those very often. So let's take a look. In this unit, we're going to explain and use the term rate of reaction. What do you think rate of reaction means? Talking about that. What is rate? We're talking about how fast a reaction happens. We have not yet addressed this. We have addressed how much energy is released or absorbed in a chemical reaction. We have not addressed how quickly that reaction occurs. And that's what we're going to address today. Yes? Yeah, go ahead. There should be also Kleenex if you need it. Frequency of collisions. Frequency means how often collision. Can you put the ball down, please? Or I'll just take it. Collision means, like a ball actually, collision means you've got two things that are hitting each other. That's what a collision is. The effect of concentration, I know that's an evil word for some people, concentration, and pressure changes on the rate of a reaction. So that's our second thing. So let's explain stuff, words, explanations. 8.1.3, put a star on it. This is new for the 2022 syllabus. This was moved from A to AF. Meaning this used to be taught in the A-level course and has since been moved into the AS chemistry class. They use experimental data to calculate the rate of reaction, including graphing. So this includes graphing, which you'll see today. 8.2.1, activation energy. If you've studied bio, you've heard this term before. It's the same thing. Activation energy is the minimum amount of energy required for a reaction to take place, like to jumpstart the reaction. This is the amount of energy you got to put in the reaction to make it happen. We call this the activation energy. So for molecules to effectively collide with each other, we do the activation energy, the amount of energy for that to take place. Sketch and use a Boltzmann distribution. Has anybody ever heard of like a normal distribution in mathematics? You ever heard of that? Anybody taking probability and statistics? Like a bill? We'll be looking at a distribution today to explain the significance of activation energy. If you don't know what that is, I'll be teaching it. But it is some concept from math. And then finally, explain in terms of the Boltzmann distribution and frequency of collisions. What is the effect of the temperature change on the rate of the reaction? And so today our main goal is to go over speed of reaction, how fast a reaction goes. You will need a calculator today, so have your calculators out, and you will need a ruler. I also suggest pencil because graphs and diagrams should require the use of a pencil. And so we're going to go ahead and get started. For graphs and diagrams, you're allowed pencil on the day of the exam. For like the other stuff, it's pen. Like solving questions like this is pen. But graphs and diagrams, pencil. And also multiple choice is pencil. Okay. We'll talk more about that when we get closer to exam time. But there are certain times where you're allowed to use pencil. Making a graph is one of them. All right, so before we get into speed of reaction, there was one type of question you'll notice I left up two questions. I kind of see the room to see if you're kind of tired and decide if I need to cover these additional questions or not. Last class, I left these off and let you start working on the assignment a little bit early, but we still have to cover them. So there was one application of Hess's law we had not yet looked at, which we're going to look at now. And when I studied Hess's law, I actually learned it like this. Take a look at what's going on. They give you two chemical reactions, and they give you each of these enthalpies of reaction. They tell you that when two carbons combine with two hydrogens to make C2H4, the reaction requires 52.2 kilojoules per mole of energy. C2H2 plus H2 goes to C2H4, releases negative 175.8 kilojoules of energy. Then they ask you, well, here's a new reaction. What's this enthalpy change? And so they ask you to come up with the enthalpy change of a reaction that is some combination of other reactions. Let's take a look on how to do this. And so here's the idea. We have to combine these reactions in such a way to come up with this reaction. So take a look at the first reaction. You see the two carbons there? What do you see in this reaction that's the same? Are there two carbons here? Yeah. So that's actually exactly the same. What do you see here versus here? But we see these two carbons, they do match. Take a look now at the second reaction. What do you see is happening in that one? Compare the second reaction to the reaction we're trying to look for at the bottom. What do you see is the difference? C2H2 doesn't. Because on this reaction, C2H2 is on the reactant side, and in this reaction, it's on the product side. So this is actually a reaction that needs to be reversed in order to end up being this reaction. Because in order for this to match here, it's going to have to be reversed. Also, notice if you do that, the C2H4 will go on the other side. So what happens if we reverse this second reaction?
And the H2 doesn't match.
So write your first reaction again, which I'm going to do. 2H2 goes to C2H4. And let's write that second reaction to match the C2H2. So reverse it. What do I mean by reverse it? The reactants become the, and the products become the reactants. So we're going to switch it. So now it's C2H4 goes to C2H2 plus H2. The question is, if I combine these two reactions together, once I've reversed it, will I come up with this reaction? What do I mean by combining reactions? I think we did this back in redox. All of your reactants, you write them, and all of your products, you write them as one reaction. Do you see anything that cancels out, first of all? If I have 2 carbons plus 2 hydrogens plus C2H4, and if I have C2H4 plus C2H2 plus H2, is there anything that cancels? Doesn't that cancel? Is there anything else that cancels? Okay, let's write what we have left.
1H2 you can get it out. So
Yeah, 1H2 is canceled, right? Because this is a 1 and this is a 2, so both of them have 1 in common, right?
you can
So
just take
this
out the
would cancel out and become just H2. Right, what's left? 2C plus H2 goes to C2H2. Does that match this reaction? All right, so let's talk about the math. They're asking for a number here. They're asking for what is the enthalpy of these combined reactions. If you reverse, we had to reverse this second reaction to make this work out. What do you think happens to this delta H here?
The positive.
Instead of being negative, it would turn into, so this would change to positive 175.8 because we had to reverse the reaction. So instead of energy being released, the same amount of energy would have to be put in. And so once you've done that and you combine these reactions, you actually can combine the delta H's as well. So we would be combining 52.2 with 175.8. So 52.2 plus 175.8 is what answer?
2.2.
And the answer is B. That's it. We're going to do another one just to make sure we've got the idea. This is the last strategy with enthalpies that you need to be aware of. Because I usually see it on paper 1, but it could actually even show up on paper 3. They could give you 2 different reactions where you have to do the foam cup and do the calorimetry, the enthalpies, and then you have to figure out how to cancel them out to get the enthalpy of a different reaction. Let's try it again. I'm checking to see, I still see some writing, so I'll wait a little bit. So go ahead and see if you've got the idea. These 2 reactions have to combine to become the reaction that they're looking for. So you have to figure out what to do to these 2 reactions so that they will combine to give you this reaction. I'm going to let you think about it this time because I worked through the first one myself. So see what is different between this and this. How can you combine those reactions and make one that I put a box around, one that they're looking for the delta H for? I'll let let you think about it first. Try it yourself.
This is the reaction reverse, right? The second.
This one? Second one must be reversed. It has to be reversed. Because you need Na2CO3 to be on the product side. So take a look at this first. NaHCO3. Look at the first reaction. Do you see NaHCO3 in that one?
Yes.
Do you see any difference between NaHCO3 in the first reaction and NaHCO3 in the reaction we are looking for the
There's
chemical
two.
change of?
There's two NaHCO.
Double. So that means what would you have to do to this reaction to
Double?
make it match? You would have to multiply by 2.
Oh, so then the enthalpy change will also be multiplied by 2, right?
Right. Because if this is the kilojoules for 1 mole, but now everything's been multiplied by 2, now this also has to be multiplied by 2. Let's take a look at the second reaction. So we checked this. We got this now to match. On the second reaction, what do you see? Na2CO3 is on the product side here, and in your elementary reaction that you're trying to make into, like, combine these two reactions to make this reaction, where is Na2CO3 right now?
Reactant side.
So you have to change it from reactants to
Product.
products, which means you have to
Reverse.
reverse. If you reverse the reaction, that actually means you have to change the sign of this. So now what I do is I rewrite my reactants and products to make sure it cancels out to become what I need it to be. And so I'm going to distribute this to everywhere. You agree? 2 multiplied by the whole thing. So I get 2 NaHCO3, and I'm eliminating states of matter because I don't want to write that extra stuff. 2 HCl, 2 NaCl, 2 H2O, and 2 CO2. Yes? The second one, what did I say we needed to do?
Reverse it.
That means that these products are now the reactants. So we would write 2 NaCl plus H2O plus CO2. And what are my new products?
C.
These are, it's reversed. So these are the reactants and these are the products. So Na2CO3 and 2HCl.
Everything down.
Will these two, when I combine them together, using the strategy that I said, multiply the first one by 2 and reverse the second one, will they cancel to become this?
Yes.
Let's just show it, right? So is there anything that can cancel, straight up cancel?
2 HCl.
Anything that's the same on the reactant and the product side can cancel. So HCl, there's 2 of them here, there's 2 of them there, get rid of them.
NaCl.
Anything else we can get rid of. NaCl is goodbye. Like it's on both sides, it's out. Anything else we can cancel at least one of.
H2O and CO2.
We can get rid of one of these and change this to a 1.
And CO2.
And we can get rid of one of these and change this to a 1. And then we write what's left, which is 2 NaHCO3. I don't think anything else, right? Products,
Na2CO.
Na2CO3, 1 water, and 1 carbon dioxide. Is that what's there? So we know it works. Now we got to do the math. So what's the math?
Negative.
Multiply this by
2.
So the enthalpy is also multiplied by 2. And so you do 2 times negative 38.97, which is?
Negative 77.94.
Yes. Negative 77.94. And the second one?
It's just 96.59 positive.
Positive. Now, if you can combine these reactions together, the important thing to recognize here is you can also combine their enthalpies together. If you can combine the reactions, you can combine the enthalpies. So you literally just combine these numbers, and what is your answer?
B and C.
melting point, fix back, and then this is Q7 on the homework. Is this strategy?
Oh, you have to do that for Q7?
Yeah, you were supposed to do something like this for Q7 to get the right answer.
This is what I did. But that's right.
So miss, in this type of questions, couldn't we just reverse the equations
So let me check later.
add the numbers?
Yes.
Instead of-
Yeah, you don't have to do this proof. This is just proving that it'll work. If you can figure it out, it multiply this by 2, reverse it, cancels out, then you just combine the numbers perfectly and get the right answer. This is just showing that it totally makes this. This is me proving that it makes that. Yes.
Where's the 2 instead of 1 in the top?
Because multiplying by 2, right? If we multiply NaHCO3 by 2, we multiply everything by 2. Distributive property.
So that's 2 and
Everything is doubled on the first reaction.
right. The reason you're doing is
Because I need to match. This has to match that. I have to match to make this.
okay.
I have to make this.
And then you match that with the top.
Right.
With the top, yeah.
You want to make that reaction happen. So we're combining other reactions to get to that reaction. So I had to compare this and I have to compare that to get my products that make sense. Yes.
The bottom reaction.
Yeah, I can explain that. So the idea is that this reaction, sodium carbonate plus hydrochloric acid, makes these products. This reaction releases 96.59 kilojoules of energy. But if we do the opposing process, you have to reverse the reaction. So if I make these the reactants and these other parts the products, when I reverse the reaction, instead of it being exothermic, it would have to be endothermic. Instead of the energy going out, it would have to be put in.
So
But they're the same amounts, so the number would be the same, but the sign would be changed.
the one has to be positive.
Does that make sense?
The one has to be changed always.
You have to compare.
And how would you tell if you had to add?
You look at what's here versus what you have. Like it's literally, the idea is you have to check your reaction, check the reaction you're trying to make the enthalpy for, like the new number, what they're looking for, and then you have to see if it's the same or if it's different. If it's the same, you do nothing to it. If it's different, then you might have to multiply or divide or reverse. So it's you have to compare. Yes. Go ahead. All right, so that was the last thing in enthalpy is combining elementary reactions together to form other reactions. We'll see this again when we do review. But try that homework question and see if you can get the answer for it. It was question 7 on homework. Yes.
For the first reaction, like they're different. So when you multiply by 2, it's still positive.
What do you mean different? I'm comparing this reaction here to this reaction here. And I'm comparing this reaction here to this reaction here. I have to combine
So you always
these
compare-
2 reactions both to this one,
So you always compare the given, the two given to
to
the.
the reaction I'm trying to make.
I did it wrong.
So I'm not comparing this to this. So I'm only looking at what's here versus what's here.
You have to learn this.
So NaHCO3 and NaHCO3 is also here. So multiply by 2 to get that. And for this second one, that's where the Na2CO3 is at. So that's why I have to reverse it to get it on the front. Kind of complicated. All right.
They're the same, right?
Okay, so we're gonna go ahead and move forward. That's the end of enthalpy, but we're not gonna leave it behind because we're gonna review next Tuesday, right? And there's also tutoring next Tuesday, and there's a test on Thursday. So let's go ahead and get into speed of reaction, new stuff. Should be a welcome change. Intro to kinetics. So there's, I guess, good news and bad news. Kinetics is the study of speed of reaction, speed is, again, math, right? When we talk about how fast something goes, we're once again addressing a math question. This is quantitative in nature. And so there is a formula for rate, and you should go ahead and know this. Change in concentration over change in time. So go ahead and write the triangles. I have taught you at the beginning of this unit what the triangle means. The rate of reaction is defined as the change in concentration over the time elapsed. How much time has passed? We're going to talk about units. What are the units of concentration? Mole over dm cubed, or mole dm minus 3. And for science, what's the unit of time that's employed? Like, what is the standard base unit of time? I haven't really talked much about time in this class. It's actually,
Hours?
time is measured in seconds, actually. And the abbreviation for second is S. So when you see S, that means seconds in a question, like a lowercase s. It doesn't mean subway. All right, so I do want to bring up here, it's important to note when you have a balanced chemical reaction, it tells you how much reactants you need to make how many products, but it actually tells you nothing about how fast that reaction goes. That reaction could happen instantly, like most reactions we do, or it could take a long time for the reaction to occur. Not all reactions happen really fast. Unfortunately, this information, the rate of a reaction, is not really something you can figure out theoretically and can only be determined experimentally, and thus can be one of the types of paper 3 labs you have. Yes. Somebody's out when they come home. Or I don't see the pass. Yeah, the mom's out when he comes back. All right, so rate of reaction. What's going on? If you take a look here, the definition that you should memorize, that's in the box here. This is the definition for rate when they say define. It's the change in the amount of concentration of a particular reactant or product over time. Take a look at this graph. This graph is time versus number of molecules. And you'll see the colors here. Unfortunately, I don't have the money to always print in color for you. So the colors are here, but they're not printed in color on your paper. But if you can see here, this is purple. Purple represents reactants, and green represents products. So that's what the colors are meant to represent to you. The purple particles here are your molecules of reactants, and the green are your molecules of products. So what happens in a chemical reaction over time? Your reactants turn into products. But it doesn't necessarily happen instantly. It happens over time. And so as your reactants effectively collide with each other, they turn into products. And you can see there's two graphs here. The graph for purple, the number of molecules over time, it decreases. What does that mean to us? The amount of reactants does that increase or decrease over time? Decrease, right? The amount of reactants decreases over time. And the amount of products? Until all of your reactants are converted into products. Assuming it's not a reversible reaction. So assuming that this is a reaction where A just turns into B. It's not reversible. This is what happens. Your reactants are converted into products. Will you be asked to make graphs?
Yes.
Quite possibly coming up real quickly in this lesson, and even in the lab, like I said, you'll you'll be asked for graphing in this unit.
What's the lab gonna be about?
Rate of reaction is the best way I can say it. You'll be determining the rate of a reaction on Friday of a specific chemical reaction. All right, before we continue, this checkup is actually from the textbook. And remember, the standard was moved from A level to AS, so this used to be in the A level. In the blue textbook, if you have the blue textbook, this is right at the beginning of chapter 22. This is one of the standards, though, that was moved from A to AS. And so they ask you here to convert the following rates into their proper units of what? What is this?
Mole.
Concentration over time. Or moles, dm minus 3, s minus 1. So let's see if we can do it. Convert the following rates into the proper units. I've got grams of iodine consumed in 1 hour, and in a volume of 1 decimeters cubed. When they give you this here, they're actually telling you what goes on the top and what goes on the bottom. They're telling you that the rate is when you have the moles on the top, because moles is to the power of 1, the dm cubed on the bottom, and the time on the bottom. So you may want to rewrite this out like this so you understand the math you're going to have to do. Before I can begin, I have to check to see if what I'm provided is in the right units. What's the first thing I'm given? Grams of iodine. Is that right?
No.
What does it need to be in? What do you think of these 3 things I need to change grams to? Grams should be changed to moles. That's a thing. We got to do that. So before we can find the rate, we first have to get the right units. How do I change grams to moles? Perfect, right? Moles is grams divided by MR. 0.254 divided by molar mass. What is molar mass of I2?
I2 is 253.8.
126.9 times 2. So 253.8. So this is going to be, do I have to write out 0.001000788?
No.
Where do I cut that?
0.001.
I agree. I would cut that there. We're good with that? Now what? I've got the moles. Do I have dm cubed?
Yeah.
Do I have seconds?
No.
So I have to do another change. I have to do hours into seconds. Well, how do I do that?
Multiply by 3,600.
1 hour has 60 minutes, and 60 minutes, each minute has how many seconds? Right. I'm just writing the official strategy. But if you remember 1 times 60 times 60, that's what you got to do. It's 3,600 seconds. Now I've got the seconds. Now I've got the moles. I've got the dm cubed. So can I solve this?
Yes.
So rate equals, what number goes on the top for moles?
1,001.
And then on the bottom, we've got 1 for dm cubed and
36.
3,600 for seconds. Go ahead and solve it. It's literally just 0.001 divided by,
36.
it's gross. You see the number? Do it in your calculator.
Oh.
I would not write that. I would change that to scientific notation. How do we do that?
2.78 times 10 to the negative 6.
Off by 1. How do we do that?
10 to the negative 7.
Rate equals 2.78 times 10 to the negative 7. Right? What's the correct unit? Mole, dm minus 3, s minus 1. How do you change that 0.000000278 number to scientific notation in your calculator? Can you do that? Remember, it's one of the things in Create I implored you, if you were in Create, and to be able to figure out how to do it. Because if you count your zeros wrong by 1, it's wrong, right? So it's better to write in the signs. So check to see that you get the same answer as I did, and then we'll continue. Look at me! Look at me! I'm so excited. It's coming back in just a couple weeks. 0.440 grams. Ethyl ethanoate. They didn't give you a formula for that. Should they feel guilty? Why didn't they give you the formula for that? Because you could figure that out, can't you? What's ethyl ethanoate? So, ethanoate. What type of functional group is this? Ester. So it's got this structure, right? The ill side is this one. CH2, CH3. The OH side is the other one. CH3. What's the molecular formula of this? What's the molecular formula of this? What's the molecular formula of this?
Oh, ethyl ethanoate. So that would be CH4.
C4, H8, O2. I need this to get the molar mass, right? Question? Okay. So, again, I need the moles is grams divided by MR. The grams is 0.440. What's the MR? 4 times
12.
12, 8 times
1.
and 2 times. Add all that up. I get 88.
Yeah.
So we put 88 on them. And what are our moles now? I get 0.005 or 5 times 10 to the negative 3. Either of those is fine. Good so far? What are they asking us to do again? Find the rates in the units of moles, dm cubed, and seconds, right? That's what they're asking for. We've now got the moles. What else do we need to do? Do we have cm to dm, right? So we know 0.005 is on the top. To change cm to dm, I do expect you can do this quickly. I don't need you to show your work. Cambridge doesn't either. They expect you to know that you can do this. And it's going to be 0.4. We're good with that? And then seconds. You don't have to show your work for this either. You've got 1 minute. How many seconds is that? So you just plug that into your calculator to get there. So it's 0.005 divided by 0.4 and 60. Do you get the same thing as I do? I get 0.000208 or 2.08 times 10 to the negative 4. With the correct units. That's the rate. What do you notice about these rates so far? Are they very large or very small? If I see exponents that are negative, that actually means they're pretty small. Those are small numbers. Good so far? First type of calculation you need to be able to do is unit work. This is like that mole stoichiometry stuff. Next thing, you need to be able to calculate what's called an average rate of reaction. Average means an average over time. In order to calculate an average rate of reaction, you will need to read this from a graph. So this will need to be determined from a graph. And the way that you do this is you calculate the change in concentration. Yes. Yes, you may. The change in concentration over time. So that's we're going to call delta A over delta T. We're going to take a look at a question of what this looks like, what you would be asked to do with the graph, and how this is actually something where that prerequisite of math is about to come into play. Remember, there's actually a prerequisite of Algebra 2 for this class. They don't require you take ACE Math for this class, but it actually is quite helpful if you have or are taking ACE Math because it helps you link ideas together. Let's take a look at this question, and we'll see what to do. This is from the 2021 test. They were previewing, before they changed the syllabus, they actually gave this question before they changed the syllabus to add the standard, which I was like, but they do that often when they're about to change the syllabus, kind of like to just throw test questions out there, and then they make it less points to pass. So this was actually given in 2021, even though the standard was added in 2022. But it wasn't many times. So they can have. Aqueous bromine reacts with methanoic acid to form hydrogen, bromide, and carbon dioxide gas. They tell you this reaction can be measured by measuring the concentration of bromine over time. Before we start, I want to tell you there was actually a mistake in this question. I'm going to correct it now. I forgot to tell my classes last year. There's a mistake in the printed graph. And I wonder if they gave everybody extra points because of that. And so I'm going to tell you right here, in your work, you may not be able to see very well anyway, right here, 2 times 10 to the negative 5. The misprint is to write that it's 10 to the 5th. It wasn't 10 to the 5th. It's actually 10 to the negative 5. There's a misprint in this question. But it's one of the only questions I have for AS that are on this topic, so I can use it. So fix it in your work. It's BR times 10 to the negative 5. They tell you that over time, the bromine concentration, is that increasing or decreasing? Decreasing. And what they ask you to calculate, so pay attention to what they're asking for. The average rate of reaction over a specific time. What is the specific time? So from what time to what time? 0 to 600. Like the whole graph, right? So then how do we do this? Take a look at what we have here. Change in concentration over change in time. What are we technically being asked for? Change in concentration over change in time. Let's think. Concentration is on what axis? Math time.
No, what?
That's y. Y2 minus y1. What is the axis of time? X. So x2 minus x1. Does this ring a bell? Is a formula you might have ever used in your life? This is literally the slope. The formula is the slope. The slope of this line, actually, the average slope of that line. It's a math formula. So if you know math, then you know what to do. What would be your first point that you're looking? At a time of 0, what's the concentration? At a time of 0, your concentration is 100 times 10 to the negative 5. Because it's concentration times 10 to the negative 5. Are you following me so far? 0 being x1, and 100 times 10 to the negative 5 being y1. X1, y1. It's important. Math. So what's happening at 600 seconds? What's the concentration at 600 seconds?
10 times 10 to the negative 5.
It would be, I think it's 10. Look at it closely here. Let me see if I can zoom in. You think 10? Because it's 1, 2, 3, 4, 5 points between 0 and 20. So each one goes up by 4.
So that's 12.
So it's actually 12. It would be easier to read on a bigger graph because when I was reading it on the paper, I also had thought 10, actually. But when you zoom in, it's actually 12. But it's that point right there. And so 12 times, it's then at a time of 600, the concentration is 12 times 10 to the negative 5. And this is called your x2 and your y2. So to find the average between 0 seconds of time and 600 seconds of time, you are actually to find the slope of the reaction, and that is the rate of the reaction. So then what's the math here? What do we got to do?
We have to subtract 12 times 7 negative 4 and 10, 100 times 7.
Over 600 minus 0. And so go ahead and do that. Does the method make sense? Change in concentration over change in time. I had done this earlier. Minus 100 times 10 to the negative 5. And then divide that by 600. See if you get the same thing as I do. There's a lot of zeros again. Welcome back. It's another small answer. See if you get the same thing. It's better to write your answer in scientific notation so you don't miscount your zeros. Negative 1.47 times 10 to the negative 6. What are our units? What are the units? What are the units here? Top is mole, dm minus 3. This is seconds. What are the units? Mole, dm minus 3, s minus 1. They're always the same, actually. Changing concentration over changing time. When the s comes to the top, you give it s minus 1. Another one. This is totally fine. All right, how are we feeling? Changing concentration over changing time. So that's method 1, is if they ask for an average. You want to circle that word average. That means that you're just employing this strategy where you find the initial concentration, you find the final concentration, the initial time, and the final time, and you subtract them. That's the first type of question you can ask. The second type, which is the more common type, is the following. Instead of being asked for an average rate of reaction, you could be asked for something called the instantaneous rate of reaction, which means the reaction at any point in time. They could ask you, what is the reaction rate exactly at 100 seconds? What would you do then? And so you're going to get your ruler out. It's about time to use that ruler. And I just copied this from the book to show you what's going on before I teach it. If they ask at a specific point in time to find the rate, it's called the instantaneous rate of reaction at that specific second. But how can we get the reaction rate at a specific second in time? If we've got a graph, we've got the ability to do that. And this is where that calculus will come into play. Yes. What? Yes. So, yes, but we will not take a derivative in this class. The way that we are going to do this is we're going to draw a tangent line. And the slope of the tangent line, that is what we call the derivative, right? So technically, but what you're going to have to do is on your graph at that point, you draw what's called a tangent line. A tangent line is basically the slope at that specific point. So that a slope at that specific point in time, we call that the tangent line. And so you draw a little tangent line, and then you have to make your mark on the x-axis, and you make your mark on the y-axis to to find your points you're going to subtract for your slope that you're going to determine. And so I'm going to show you this from scratch, of course. But I wanted to have it printed. I literally just took a picture of the textbook and put it here. This is, again, it used to be an A level. It's been moved into AS. Let's take a look at how we would do this from scratch. Check up 3. It says, plot the following data for decrease in cyclopropane concentration over time. So this is time, and this is concentration. What are our axes for rate? The x-axis is time, and if they give you minutes, you can use minutes. Just you'll have to consider that in your, if you do math work. And your y-axis is what? Concentration, right? So this is going to be concentration of what specifically? What are they asking for? Cyclopropane. Isn't that fun? More organic stuff. Could you put cyclopropane as a triangle in there if you really wanted to?
Yeah.
That's what cyclopropane is. So if you want to fence around, I guess. Cyclopropane, right? So far, so good? One of the decisions you will have to make, you need to graph along. Make sure you're graphing along. One of the decisions you will have to make is how to choose your axes. Whenever you have a lab, one of the decisions you're going to have to make, and you saw this in the lab you had a couple of weeks ago, is you had to choose your axes. And so we need to choose our axes in such a way that we can get a little bit past the time in the information here. So the time goes up to 40. We can even go to 40. It doesn't say they have to go farther. So how can we break this graph up from 0 to 40? It would be 0, 10, and 40. In statistics? Oh, great that you're in statistics. Later on in today's lesson will be very helpful that you know some statistics. All right, so we got this so far? That's the time. Now what about concentration? Where should I choose to go up to? It says it's between 0.33 and 1.5. So what would make sense? To go up to 2. That makes sense. So I would do, this is 0.5. This is 1.0. This is 1.5. And this is 2.0. How does Cambridge mark? You have to fill the graph at least more than halfway on both the x-axis and the y-axis. So if you end your 1.5 like here, they're not going to give you a mark for graphing correctly. So you have to make sure that you fill half the space on both sides. You remember that from when we did the last lab?
Yeah.
All right, so now that we've prepared this, we know that these are going to move up by 0.1, and these are going to move up by what? The time. The time's going to move up by 2. That's the way we have our grid. So let's go ahead and see if we can graph this data. First point, at a time of 0, the concentration is 1.5. Time of 0, concentration 1.5. We put an X. Good with that? Remember, X is not dots for Cambridge.
Oh, yeah.
X is not dots. Use X's. Next one. Yeah, I graphed it. By the way, random info. Graphing data like this would be a 2-mark question on a paper 5. Do you know what paper 5 is? It's A level. They have 2 papers. One's paper 4, one's paper 5. Paper 4 is the theory paper, like your paper 2, and paper 5 is not a wet lab, but you're given questions with experimental data. So like this would be an example of a 2-mark question on a paper 5, where they give you the data and they're like, hey, graph this. And you have to graph it correctly for 2 marks. Anyway, So that was the first one. The next one is 5 and 1.23. At a time of 5, we got a concentration of 1.23. So where's 5 here?
In the middle of 4 and 6.
4 and 6. And 1.23. And of course, you can do a little bit of estimation. It's got to be between 2 and 1.2 and 1.3. And it's going to be, remember, you have a ruler you can use, so you're going to do better than me. Something like that. Second mark point, second plot point. Next one, 10 and 1.0. Still following me? 10 and 1.0. That's an easy one. That's here. Next one, 15 and 0.82. 15 and 0.82. Right here. 20 and 0.67. 20 and 0.67. What's the next one? Yes. Go ahead. 25 and 0.55. Here. 30 and 0.45. There. And 35 and 0.37. And 40 and 0.33. Something like that. Once you've drawn your graph, so it says to draw your graph, plot the following data. The next thing you would want to do is draw a line of best fit. What does that mean again? Not a straight line. You need to encapsulate these points as best you can. If you look at the other rates of reaction, take a look at how they are. They're curved lines of best fit. It's a curved line of best fit. There will be a curve in your line of best fit. So do you see it? Because it tapers off. It starts to go like this. So my line of best fit, and I'm going to do a terrible job because, but I'm going to try to encapsulate these points as best possible. Like a smooth line as best possible. Something like that. Line of best fit. So far, so good? Line of best fit done. Now, how do we draw the tangent line? And we're going to take a look at the question. What does it say on the next slide? Calculate the rate at 10 minutes. So circle the number 10 minutes. We want the rate at exactly 10 minutes by drawing a tangent line. So now you get out your ruler. You go to 10 minutes. Go to 10 minutes. And this is what you need to do.
Draw a line up the graph.
You draw a line that hits both axes, your x and your y axes, that just touches the graph at 10. That's what we call a tangent line. It is a slope at that specific point. I can't really do it because if I do the ruler, it actually messes with the screen. But it's where your line is going to be a straight line. It's going to be a slope like this, where it just touches and goes straight down like that. See if you can do that on yours. That is a terrible thing. Probably the first one. Let me see if I can try that again. It's got to. Exactly at 10. Again. Something like this. Something like that. That will be a little bit better. It can't cross the line. The thing about the tangent line is it can't cross your graph. Again, I did a terrible job myself. So it looks like it would be something like this. It's got to be straight, which is why you use your ruler. That's closer. Let me see what you all got. Because I can probably guess yours is good. Let me try yours. can't cross the line. So this is okay. Let me look at yours. Good. Let me look at yours.
Both.
Yes. Good. They can't cross through the line. Can I see your tangent lines just to make sure you've got the idea? So yeah, it goes at 10. You basically touch it and draw a line like that. So it hits both axes. So at 10, you don't want to connect the dots with this line. You make a smooth line through it. And then you go ahead and take a look. Let me look at yours. Yours is good. Let me look at yours. So as long as it doesn't bounce over, like cross over that line, it's good, so this is fine. And you're gonna see,
It hurts.
as long as you go like 10 and you hit it like with that slope, that's fine. And then let me take a look at yours. Good. And yours is a little bit exactly at 10. So exactly at 10 would be there. See it? So it basically bounces at that point and hits the two axes. All right, so I'm going to use my data, but remember the data is going to be based off of your tangent line. So Cambridge gives some room for, it has to be like this, right at 10, whatever you have at 10. It can't cross that line, it has to bounce off of it. So it's more like this, like how I've done it. You just have to extend yours out the rest of the way, so like to there. All right, so now what do? You find where the tangent line intersects on the y-axis and where the tangent line intersects on the x-axis, on both axes, the y and the x. You find these points. They're going to be a little bit different for all of us. And Cambridge allows for some room for error. But you find these two coordinates. Mine are 1.3 and 0. And when it's 0, it's 30. I would go 39. Yours were anywhere that I observed from 32 to like 38 is what I saw you all had. And those are all fine. Use your numbers. Now what do I do to find the rate? What do I do? y2 minus y1 over, rise over run, we call it, the slope. So what's my y2 and my y1? y2 is 0. 0, 1.3, and this is 39 and 0. What's my y? I'm going to just put them out. 0 and 1.3 is what I got. And I got 39 and 0. So what's my math here? 0 minus 1.3 and 39 minus 0. And so negative 1.3 divided by 39. Or something close to that, depending on your tangent. I get, oh, that's an interesting answer. I get negative 3.3 times 10 to the negative 2. So you should get something around that line. But make sure you know the strategy. Take the 2 points you have, do y2 minus y1 and x2 minus x1 to get the answer. All right, I'm going to skip B so that we can get to the other part of this unit. If I do it again, I'll do it on Friday before the lab. But we have some other stuff to cover. And the more that I can cover today, the more time we have for the lab next class. So we have some more material. But we're done with math for now. So hopefully this other topic will be forgiving a little bit more. All right, here we go. Collision theory. This is extremely important that you know. Collision theory. What does collision mean? Can I have my rulers back since you're done with them? What is collision theory? What is a collision?
Collision is when two things collide.
So,
No way.
let's talk about like one of the most simple chemical reactions we can do. We got some hydrogen, we got some chlorine, and we make some HCl. How did this happen?
They combine.
We know that hydrogen combines with chlorine, but how? You've got a bunch of this. And you've got a bunch of molecules of this. And they're just floating around. These are both gases, right? So how, if H and Cl and Cl are in a container, how do they become HCl in the first place? So in gas phase, molecules will eventually collide into each other. And if they collide with enough energy and in the correct orientation, then a chemical reaction will occur. And that's actually the basics of collision theory. So this is what we used to explain. And we will be explaining the effects of changing concentration, the temperature, surface area, and adding the catalyst into the rate of the reaction. You should memorize this. In order for a chemical reaction to happen, the molecules involved or the species involved need to effectively collide into each other. What do we mean by effectively colliding into each other? Well, I'm about to explain that. They have to collide, but it has to be effective, meaning when they collide, they meet, they're now together. An effective collision. So, I'm going to go ahead and describe what that actually means. So, an effective collision is one where your particles collide with enough energy going in and the correct spatial orientation, meaning facing the other molecule in the right way, so that the correct atoms will connect to each other to make products. So spatial means like 3D in space. The atoms have to be connected a certain way. An ineffective collision is one where two molecules approach each other, and when they collide, they just bounce right back off. No reaction takes place. Molecules just bounce off each other. Not effective. That's what we call a not effective collision. No products are made in an ineffective collision. So you have to have an effective collision to change reactants into products. So an ineffective collision using the same thing. If this can happen if your molecules are too slow, like they're moving very slow, so not enough force to collide effectively, or they're in the wrong orientation. They're not facing each other the right way. And so in this case, the reactant molecules will remain the same. Whereas if you have a successful collision, this is one for NO2, and NO2 and another NO2, your molecules approach each other. They collide in the right spatial orientation with enough energy, and it forms a covalent bond between, in this case, the two nitrogens in the middle, forming N2O4. So this is N2O4. I know it's fuzzy. So this is NO2 plus NO2. They approach each other the right way with enough energy. Bam, we now have N2O4, right? That's the idea of what goes on. So then what ties into this is something called activation energy, which in chemistry we are usually not going to write out the whole word, we're just going to write it as EA, E subscript A. And I always hear that in my head. Whenever I say EA, I think EA Sports is in the Like, I don't know if we're programmed that way. Activation energy, we do write it. This is how you'll see it on a Cambridge exam as EA. And not cool. But it has to do with soccer, that's energy. The minimum energy that colliding particles must have for the successful collision to take place. So in order to successfully collide, molecules must contain a certain amount of energy. Or a certain amount of energy has to be put in to that reaction. And so once those molecules have enough energy, they're going to collide and you make your reactants turn into products. What does it look like? This may be familiar to you, especially if you've studied biology. So pay careful attention, especially if you haven't. This also may be familiar to you from the earlier part of the unit. We looked at something called an enthalpy profile diagram in lesson 1. And I told you that the energy of the reactants, because enthalpy we can, for now, say pretty much just the energy, right? This is the energy of the reactants, and this is called the energy of our product. And the difference between the energy of the reactants and the energy of the products is called the delta H. This enthalpy is exothermic because the reactants are releasing energy to become products. But there is a missing part of that graph. For the reaction to take place, there actually has to be a deposit of energy. And so we call this the activation energy. The activation energy will always be positive. EA is always positive. It always requires energy to kickstart a chemical reaction. Some energies will require more energy than others. And so you'll observe this as either a bigger hill or a smaller hill. I always think of this as riding a roller coaster, where you start here, energy in, energy in, energy in, energy in, energy in. You get to the drop, energy out, tons of energy out. I always think of it like a roller coaster. You follow along. All right, types of questions. What can we get here? Paper 1 first. And there's usually a couple of questions, 2 to 3 on every paper 1 on kinetics. And they are easy questions typically. So make sure you're paying careful attention. Reaction pathway for a reversible reaction is shown. Reversible means this. So you may want to just write that down, because we're not really talking much about reversible reactions until the final unit. So it just means that as the reactions turn into products, the products can turn back into reactants. So which statement is correct? First statement says, activation energy of the reverse reaction is 8. Is that correct? So this is what we call, when we look this way, this is what we call the forward reaction. That's what Cambridge is going to use. If we look at it the opposite way, we call it the reverse. Remember, in the reverse reaction, your products are actually your reactants. It's reversed. It's reversed. So the reverse reaction actually means you're looking starting here and ending here. What is the activation energy for your reverse reaction? What do you think?
For your reverse reaction, 80?
80. Right?
Oh, yeah.
Because it goes from here to here. The 50 plus the 30 is 80. The energy of activation for the forward reaction is 30. Because that's how much energy has to be put in to turn your reactants into products. The energy of activation for the reverse reaction is actually 8. You need to put in that much energy to go from your products back to your reactants. So is it statement A?
Correct.
Good answer. Can we prove why the other ones aren't right? Forward reaction, what's the enthalpy change?
30? No,
Remember, enthalpy is the difference between reactants and products. So the enthalpy of the forward reaction is See if that makes sense.
Oh.
Because energy out. The enthalpy of the reverse reaction would be positive 50, actually. And so none of these make sense. All right, so how do we speed up a reaction? How do we use collision theory to support our evidence that we can speed up a reaction? You were probably told in pre-ACE chemistry, if not before, that if we want to make a reaction go faster, we could stir it. Do you remember that? We could heat it up. So in some way, we have to increase the frequency of collisions. We have to get those particles to collide with each other more often, so there's a more likelihood that you'll have an effective collision. And we need a proportion of the particles with energy higher than the activation energy that have enough energy to turn from reactants to products to increase. And so the final thing we have to learn today, and we'll talk more about a catalyst next class, is something called a Boltzmann distribution. So you're going to see the definition for catalyst on the next slide, but the next lesson on Friday, the one where I do a short lesson, is really just going to address how do catalysts affect the rate of reaction. That's the goal of that lesson. You will have to memorize what a catalyst is. Like I said, I'll return to this on Friday. It is a substance that makes the rate of reaction go faster, but it's actually not used itself. In pre-ACE chemistry, I would have told you that it shows up on the top of a reaction arrow. It doesn't show up as a reactant. It doesn't show up as a product. And it does this by lowering the activation energy. I'll come back to this next class. Let's talk about effective concentration on reaction rate. If I add more reactants, will this affect the rate of reaction?
Yeah.
That makes sense. If I increase the concentration of what could potentially be colliding, they will collide with each other more frequently. So the change in concentration will increase the effective collision, which therefore increases the rate of reaction. And I would just remember, because I have more of them, they'll effectively collide more often. And so this increases, it'll make our reaction go faster. One of the things you'll be exploring likely in the lab on Friday is a change in concentration on reaction rate. So that's what we said here. If you need more time, I'll pause for a little bit. The other thing we have to look at is temperature. How does temperature affect the rate of the reaction? If I increase the temperature, do you think the reaction goes faster or slower for most chemical reactions? Faster. And so a lot of this unit is sort of intuitive in that way. We know that if we raise the temperature, it's going to go faster. Why? We have more energy. If we have more energy, we're more likely to have an effective collision. So before we get to temperature, let's do one quick question on concentration. Dilute hydrochloric acid with marble chips, which are calcium carbonate, give off carbon dioxide gas. Which solution of acid will have the fastest rate of reaction? Take a look at the answers and what do you think? I mean the answer choices. We've got 50 centimeters cubed of 0.5 mole yin cubed, 10 centimeters cubed of 1 mole yin cubed, or 25 centimeters cubed of 0.5 mole yin cubed. You just wrote down the answer with the arrows. What do you think it is?
Oh, 50 centimeters. Oh.
It's how much you have packed into the area that matters. Highest concentration, which here is 1 molarity, right? Will give fastest rate. The volume is irrelevant, actually. That's there to trick you. You would literally just be looking for the highest concentration. That gives you the highest rate. So the answer is the one with 1 molarity. That will give you the fastest reaction. fastest initial rate of reaction. It'll drop off as everything's reactive. But they said fastest initial rate of reaction. Like what happens at the start. All right, final thing for the day. And this is where we're going to end today and begin next class. I told you there was good news today. I'm not giving additional homework until Friday, but I do need you to finish that bond energy homework and turn it in by tomorrow night. Last thing we're going to look at. So I need your attention just for a few more minutes. Temperature. How does it affect the effective collision? In order to understand this, we have to be able to interpret a specific type of graph called a distribution. Has anybody heard of a distribution before in mathematics? It shows up in a class called probability and statistics. And so what you might have learned about a distribution is there's something called a normal distribution. Have you heard of that? Where you have
It's like a bell curve,
a
right?
bell curve. And you have the greatest proportion here. This is like the 50th percentile. And then you have less than 50th percentile and greater than 50th percentile. And those of you in ACE Math will do something called Z-scores and all kinds of fun stuff. But we don't need all that. What we do need to know is the following. Under a curve, for us, you're going to see a distribution of molecules with different energies. A distribution of molecules with different energies. It will not be a normal distribution. It will be skewed. It'll be a skewed distribution, and you're going to see it very shortly, right? But I'm going to give you time to write this down. What is a Boltzmann distribution? It is a distribution of all the molecules you have in a mixture and all their various energies. The way that I would describe it, just to kind of understand what's going on, is think about what happens. Have any of you ever made let's go as simple as macaroni and cheese or spaghetti on a stove, and you've ever boiled water? Have you ever boiled water? Boiled water is something. Okay. When you boil water, I have a question for you. Are the molecules in your pot of water all receiving the same amount of energy? Yes or no? You got a pot of water. You know that steam's going to be let out eventually. It's going to boil and steam's going to come out, right? But is every molecule being given the same amount of equal heat? Or does it make sense that the bottom, where the stove's heat source is, that's what's getting more energy, right? How do we feel about this so far? Does that make sense? So in a sample, not every molecule has the same amount of energy or being, given the same amount of heat. And so the distribution you'll see looks more like this. And so see if we can understand it. This is called a Boltzmann distribution. Boltzmann, of course, these things are named for the scientists that came up with the theory. It shows the number of molecules versus the amount of energy in a chemical reaction. And you've got a really important point here called the EA. Only the proportion of molecules that exceed the energy of the activation energy have enough energy to effectively collide. So only out of all the molecules under this curve, only these have enough energy to collide and turn into products. Are you following me so far? I'm talking about all the molecules under this. Can we link that to math, those of you in ACE Math? What is the area under a curve? If I actually wanted to calculate how many exact molecules from one point to another point were under this curve, is there something I can do? Not something that you'll ever be asked to do in this class, but something called an and integrate.
Those things are how
The tears welling up in my eyes.
I thought we were
I'm
about
not
to do it.
here to teach you integrals. I'm just here to tell you that these are actually linked ideas. The area under the curve is something called the integral. You will not have to calculate the area under the curve. But the idea that these are all your molecules that you have, you should have an idea of that. So, what does this curve tell us? It tells us that there are only a certain amount of molecules that have enough energy to react. So, there are two ways we can manipulate this curve to make more molecules react. One is we can change the temperature. So if we change the temperature, what would happen? Change temp. Like heat it up. Put it in a hot plate. Put it under a Bunsen burner. What would happen to the proportion of molecules that would effectively collide if we heat up this mixture?
It would increase.
We know they would increase. How do we show that on the graph? I think I have that right here for you. So at a higher temperature, here's what's going to happen. The amount of molecules increases. So write this. These are the extra molecules that now can react. So extra molecules with enough energy to react at the higher temperature. What else do you notice about what happens at a higher temperature? From the first Boltzmann distribution to the second one. There's not as high of a proportion of molecules at any one amount of energy. It's more like spread out. So the way we understand that is the top of the curve moves down into the right. So at a higher temperature, your molecules actually spread out. There's more molecules that have different energies. So instead of having this, it actually moves over. Your maximum peak moves over, but it also decreases. And this also naturally, so what happens here is if I increase the temperature, it'll be something like this. Depending on how I increase the temperature, I'll increase the amount of particles that can effectively collide, that have enough activation energy to collide. So that's what's being described to you here. This point right here is very important that you pay attention to. Yes. So there's the same amount of molecules. It's just they're spread over a different area. They're spread over a different area. You raise the temperature, so there's less molecules that have this very low temperature, but there's more of a spread at the higher temperature. So it always decreases the top of the graph and moves it over. So it's like it spreads out. Is the way to understand it. Yes. Not really. Not really. All right, so let's take a look if we can understand this on a paper one. This is going to be about the end. This will be the last question we do, I think. And then I think it actually is the last question of the lesson. We'll do some more on this next class along with what happens with catalysts. So, which curve, solid line, represents the distribution of energies in a gas at 500 K? What's 500 K? We mean 500 Kelvin. If the dotted line is 300 Kelvin. So dotted line is 300 Kelvin and straight line is 500 Kelvin. Which of these two graphs are correct? See if you can figure it out.
Celsius plus 270.
So your dotted line's low temperature.
Wait, no. Celsius plus 270 or plus 235?
Solid line's high temperature, right? Which one's right?
Good afternoon, Golden Lions. This is Emily. And these are your afternoon announcements.
And that.
Attention,
Down
students,
and to
here
the right
here for a
for
reminder.
the high temperature.
Where the appropriate
Okay,
school
that's the last one.
uniform.
No homework today, but finish the homework from last class. We are on track to be able to do the lab next class.
Monday to Thursday.
No, you just have to understand what it means. Oh yeah, thank you, Zed. On top of it. On top of it.
Not useless.
Alrighty. I have
No eating in the hallway.
quarterly.
Make sure you bring along.
David. Sophia.
Outside the building is not accessible.
Sophia.
All pickups and
Quarterly. Look over.
This is the
Quarterly to look over. Keep them. Janie.
The entire school students and do the right thing, such as
Mariana.
preventing bullying,
Vanessa.
following the threat, showing exceptional kindness, nomination submitted each month. Each nominee receives a T-shirt, certificate, bumper sticker, letter of congratulations.
Bravo.
Please visit www.yearbookorders.com. The order number is 21027.
We'll have a meeting Wednesday,
Yes, it was.
today.
Yay.
The EHS members will be a mandatory meeting next Monday, January 29th, after school in Mr. Labby's room.
Attention art and gardening members, we will be having a parade for March 7th.
No, just one thing. Be back on Friday for a little bit.
AV Club will be having a mandatory meeting on Tuesday, January 30th, after school in Mr. Murray's room.
And this concludes our afternoon announcement. Enjoy the rest of your day.
Adorable. Especially in the beginning when they all have
Especially when they make them balls and had
leave a little friend right there. Because the show for you to go with. But they do not yet. They made all of them in the air. I don't see you call what can sky do? 3 piece substrate. They're on a spectrum. Phosphorus? No. What can Chase do? Exactly how many electrons are in 3 P?
Go in his police car and that's it. What
about my
song?
P. 1, 2, 3.
I thought it was P3 minus, that's why. It says P3 minus here. That is for that.
Oh, no. It just says in an atom of phosphorus. They tricked you. They tricked you. Yeah. No. Yeah, if it had been those, yes, that would have been correct. But because they said atom, not ion. Actually,
I figured it
that
was
was actually kind of weird that they wrote that because they didn't. I should have got the answer.
What you guys doing?